Good afternoon, sir.
Good afternoon. Good afternoon.
Thank you for joining, sir. So, dear participants, our resource person, Professor Ram Vilas Pachori, he has joined us, and we are going to start the session 2 of the day 3 of 1 week FDP on machine learning concepts and applications. So, as far as our resource person is concerned, so Professor Ram Vilas Pachori received his BE degree with honors in electronics and communication engineering from Rajiv Gandhi Technological University, Bhopal in 2001, and then MTech and PhD degrees in electrical engineering from IIT Kanpur in 2003 and 8 respectively. He worked as a postdoctoral fellow at University of Technology of Troyes, France during 7 and 8. He served as an assistant professor at Communication Research Center, International Institute of Information Technology, Hyderabad during 2008 and 9. He served as an assistant professor at Department of Electrical Engineering, IIT Indore, in 9 to 13, then worked as associate professor at Department of Electrical Engineering, IIT Indore during 13 to 17, where presently he has been working as a professor since 2017. Currently, he is also associated with Center for Advanced Electronics at IIT Indore. He was a visiting professor at Neural Dynamics of Visual Cognition Lab, Free University of Berlin, Germany during July-September 2022. He has served as a visiting professor at School of Medicine, Faculty of Health and Medical Sciences, Taylor's University, Malaysia during 18-19. Previously, he has worked as a visiting scholar at Intelligent Systems Research Center, Ulster University, UK during December 2014. His research interests are in the areas of signal and image processing, biomedical signal processing, non-stationary signal processing, speech signal processing, brain-computer interfacing, machine learning, artificial intelligence, as well as Internet of Things in healthcare. He is an associate editor of Electronics Letters, IEEE Transactions on Neural Systems and Rehabilitation Engineering, Biomedical Signal Processing and Control, and an editor of IETE Technical Review Journal. He is senior member of IEEE and a fellow of IETE, IEI, and IET. He has served as member of review boards for more than 100 scientific journals. He has also served in the scientific committees of various national and international conferences, delivered more than 250 talks and lectures in conferences, workshops, and academic events organized by various institutes. He has been ranked at 20 in India among top scientists for 2023 in the field of computer science by research.com website, and also been listed in the world's top 2 scientists in the study carried out at Stanford University, USA 2020, 2021, as well as 2022. He has received several awards, including Achievement Award, Best Paper Award, Excellent Grade in the review of sponsored projects, Best Research Paper Awards, Premium Awards for Best Papers, IETE Professor, SBC IA Memorial Award, and Best Paper Awardees, SPA Conference 2022. Dear participants, he has supervised 15 PhDs, 23 MTechs, and 49 BTech students for their theses and projects. And as well as at present, 15 PhD scholars, MTech, 3 MTech, and 1 MS, 5 BTech are under progress. He has 284 publications, which include journal papers, conference papers, books, book chapters. He has also 8 patents, and his publications have been cited approximately 13,000 times with H-index of 62 as per Google Scholar. He has worked on various research projects with funding agencies like SERB, DSP, DBT, CSIR, and ICMR. So I welcome you again, sir, in this 1 week faculty development program on machine learning. You have spared your valuable time for us. Now you are requested to start your session, sir. Thank you so much.
Thank you very much, Dr. Saurabh for a nice introduction. And I would like to convey my thanks to Dr. Saurabh for providing this opportunity to be part of this short-term course. Thank you very much. Let me share my slides. Are you able to see the slides?
Yes, sir.
Okay. So thank you very much, and good afternoon, everyone. So today's talk is actually focused on this use of machine learning in multivariate signal processing framework. So this multi-channel signal processing, that is actually one of the important direction of the signal processing these days. This most of the signal processing that we use that is channel-wise signal processing. So in real life, we will see in this talk there are many situations, many scenarios where we find actually multi-channels, and when you process them, then what we'll do, we actually apply the signal processing channel wise, and each channel we actually separately process, and then we extract features, and then we perform classification like that. And such kind of signal processing has some actually limitations, some concerns that will be highlighted in this talk. And this multi-channel signal processing actually provides an opportunity where you can apply signal processing for all channels together. So in that way, there are certain advantages, and machine learning techniques actually that is provide you a platform where this automation process can be carried out. So in this talk, we will actually recently our group has developed two new signal processing approaches, that is multivariate Fourier-Bessel series expense based empirical wavelet transform. And in this talk, we will see this multivariate empirical wavelet transform, and also this iterative multivariate iterative filtering. So these multivariate empirical wavelet transform and multivariate iterative filtering, these two frameworks will be explained, and we will see when you use them with machine learning techniques, then you can nicely design intelligent systems, expert systems, which can nicely detect epilepsy disease from the electroencephalogram EEG signals, and also schizophrenia from the EEG signals. So there is actually a lot of applications, a lot of interest in the literature for such kind of systems. For example, like in rural areas, we don't have doctors, and such kind of systems which can detect disease in the early stage can be used to detect the disease early stage in the rural areas where you have shortage of doctors. Even sometimes urban areas we have doctors, but such methods can assist them because doctors are less and patients are many. So these systems, intelligent systems, expert systems, are very useful for developing this intelligent system, which will help the neurologist assisting their diagnosis process and in order to carry out the efficient diagnosis. So with this background, let us start this talk. So first, actually, we will see the introduction, then motivation for this research, then empirical mode decomposition briefly will be explained, and then we will see empirical wavelet transform, and then our proposed approach, that is multivariate empirical wavelet transform, will be explained. And after that, we will see its application for detection of epileptic seizures from electroencephalogram EEG signals, and then iterative filtering, then extended version of iterative filtering that we call multivariate iterative filtering, that will be explained. And after that, its application for detection of schizophrenia from EEG signals will be explained, and in the end, conclusion will be provided. So here actually, this you can see in signal processing, one of the important part is signal representation. And suppose you have a signal in your hand, and you don't know what information it has. So one of the way to extract the information from the given signal, we try to represent the signal in terms of simple signals, or with that these simple signals are known as basic signals, basis functions, or non-functions, building blocks. So one such kind of representation, that is a Fourier representation. In Fourier representation, we represent signal in terms of sinusoidal functions. So here you can see, for example, this is a signal which is actually stationary signal, which is a mixture of two sinusoids, and another signal that is non-stationary signal. So there are two frequency components from 0 to 2 second. There is a one frequency component. After 2 to this 4, there is another frequency component. So frequency is changing with time. So second signal is non-stationary signal, and first signal is stationary signal. So when you apply this Fourier transform, then in frequency domain you see in both cases you are getting this same kind of spectrum. So your spectrum is not unique because your signals are changing in time domain. So this spectrum actually needs to be unique. So motivated by that, there has been actually one important direction, the signal processing, that is known as preserving this time information together with the frequency domain. So based on that, the time frequency representation concept came in the literature, and this together with that, another direction of research has been actually taken place. That is actually modeling of the signal in terms of such functions which have non-stressing nature. So based on that, there have been two dimensions in the literature. One is actually fixed basis function based representation, and second one is adaptive basis function based signal representation. So fixed basis functions based representation, like Fourier transform, Wavelet transform, we use basis functions from our side, and adaptive basis based decomposition approaches, we don't design basis functions from our side, but on the other hand, we extract these basis functions from the signal itself. So there we use some algorithm, we use some adaptive approach, and that actually they nicely can decompose the signal into simple components. So in that way, these two approaches gives you indirectly or directly amplitude and frequency modulated sinusoid components. So this can be considered as a like more general form of the sinusoidal basis functions, where these parameters amplitude and frequency, they are changing with time. So here you can see this is a nice actually mathematical representation of AM/FM signal. Ut equals to AT e to power j phi d. So AT is time varying amplitude and phi d is time varying phase, and derivative of this phase gives you the instantaneous frequency. So this model can be used to represent narrowband signal and by AM/FM modulation model. And this narrowband signal, narrowband mathematical structure can be used to represent the wideband signal, and that actually is suitable for univariate data, univariate channel or univariate time series. So where the signal is wideband, but we can represent the signal in terms of this narrowband AM/FM components. And then this can be generalized for multi-channel signal processing. So this n-variate monocomponent signal, here you can see, so each element is a AM/FM component. So this is the vector where each element is AM/FM component. So this is like a multi-channel, and now we can say this multi-channel, multi-component nature of the data. So then this is the mathematical model. So where each element itself is a multi-component. So this is a multi-component, multi-channel signal, and then actually this is the now a mathematical framework to represent this multi-component AM/FM signal multi-channel. So this last one, that is actually more general mathematical framework for multi-channel signal processing. So what is the actually motivation for this multi-channel signal processing? In real life, you will find many scenarios where you will find presence of this multi-channel data. So, and this is also due to the advancement in the technology, it has become easier to record this multi-channel data. So like at a time we can have multiple signals, and here in this slide you can see three scenarios where one can obtain actually multi-channel data. And the first one is vibration sensors, like that data we use for ear fault diagnosis. So here actually you can see these two channels, at a time you can have two vibration signals. Second one is electroencephalogram EEG signal recording. So we use electrode cap, and when you put on the head of a subject, then at a time you can have a number of EEG signals, depends on the number of electrodes that you use in the electrode cap. So if you have 256 electrodes in the electrode cap, then you can have 256 EEG signals. And similarly, last one, that is electrocardiogram ECG signal recording, where you are putting electrodes on the chest of the person, and you can record ECG signal. And so here you can see there's multiple electrodes are positioned in the chest, different locations, and you can have different actually ECG signal from different locations. So in all scenarios, we have actually multi-channel data, and if you process them channel wise, then actually you are not considering the correlation which is existing among each other. So we are actually ignoring the correlation that is actually between the different channels. This is one of the limitation. And second one, that is actually these channels, they have visual information, but when you actually when you process them channel wise, then actually mutual information is not preserved. And when you actually use this joint analysis and joint signal processing, then actually you can preserve the mutual information, you can preserve the correlation among the channels. So that is why this is one of the motivation for going for multi-channel signal processing or multivariate signal processing. Other one these days that you have seen another direction of the signal representation, where we use adaptive signal decomposition approaches. So when you apply adaptive signal decomposition approaches to each channel, then number of components will be different. Number of basis functions that you obtain from the adaptive method will be different for each channel. So when you compare this basis function channel wise, then it is problematic because each signal can have different number of component, different number of basis functions. So due to that, actually, it is necessary to decompose by using multivariate approach so that mode alignment property is preserved. So each signal will have same number of components. So this is actually motivation for using multi-channel signal processing. And now signal processing actually started from the this Fourier transform. So we see Fourier transform. What we do, we represent signal in terms of sinusoidal functions, and these sinusoidal functions they are periodic in nature, and they actually extend from minus infinite to plus infinite, and the spread is infinite, duration is infinite. So due to that, this time localization and time resolution, that is actually proportional to 1 upon spread. And the sinusoidal functions, they have actually zero time localization or zero time resolution, so they are not able to represent non-stressy signal in better way. So in order to apply this actually the sinusoidal function of Fourier transform for non-stressy signal processing, then the short time Fourier transform, which we call STFT, it was proposed in the literature. In short time Fourier transform, what we do, we divide the signal into different segments, and each segment or windows, we assume that signal is stationary, and then actually we apply Fourier transform for each window. Then arrangement of these Fourier transform gives us the short time Fourier transform, and that way we can analyze the non-stressy signal in a nice manner. In STFT, actually, there is a problem with the size of the window and type of the window. There is no thumb rule which will suggest us what should be the size of the window for signal analysis, what is the type of window. There are many types of windows. There are different windows are available, but there is no thumb rule which will suggest us this window should be used. That is to the experience. And when your signal is low frequency component, then you require wide analysis window, and when your signal is high frequency component, then you want to have narrow analysis window. So this actually size of the window, how to decide that itself is a problem in the STFT. So that is actually what the motivation for this wavelet transform. In wavelet transform, we use a scale concept. So based on the selection of the scale, like if you want to analyze high frequency component, then we use low scale, and that gives you good time resolution. And if you want to analyze low frequency component, then we use large scale, so which gives you the good frequency resolution. So in that way, actually, we can have multi-resolution analysis based on different scales, and nicely different kind of frequency components present in the signal can be analyzed with the different resolutions. And the good thing is that is wavelet decomposition can be implemented with the filter bank. So we apply the signal, low pass filter, high pass filter, and then we get the downsample each part and get the approximate details. Again, we can decompose them. So in that way, different levels of the decomposition can be obtained. And here actually, in wavelet decomposition also, there is no rule which will suggest us how to decide the number of levels, number of level of the decomposition, and also how to select mother wavelet for the signal decomposition using this wavelet. That these are the two problems. So we are motivated by that. In 1998, Huang and others, they come up with the empirical mode decomposition kind of approach. So empirical mode decomposition approach actually, we don't design any basis functions. There is simple algorithm, and just we apply algorithm on the signal and it decompose. And in terms of simple function that we call intrinsic mode function, IMFs. So in this slide you can see this is the signal that we want to analyze, and then we determine maxima and minimas of the signal, and then we interpolate these maxima minima to get the two envelopes, maxima envelope, minima envelope, and then we average out both of them. That gives you the this instantaneous average of these two envelopes, and then we subtract from the signal. That gives you the detail. So this detail actually should satisfy the conditions which is required for the IMFs, intrinsic mode functions. So if there are two conditions specified by the Huang and others, if your IMF, intrinsic mode function, is satisfying these two conditions, then these conditions ensure that whatever these components you obtain from the signal, IMFs, they are narrow-band in nature and symmetric in nature. And then actually, if it is not satisfying these conditions, then we repeat this process again and again. So in that way, we obtain all possible IMFs from the signal, and here you can see this is the signal, and then actually this is the obtained IMF, first IMF, second IMF, third IMF, fourth IMF, fifth, sixth, seventh, eighth IMFs. And this first IMF, this represents the actually highest frequency component present in the signal, and that is also actually the lowest scale present in the data. Similarly, this last IMF, 8th IMF, that is actually that represents this lowest frequency present in the signal or the largest scale of the data. So in that way, you can have actually the different scales the present in the data in the form of different frequency components, similar to the wavelength. And this approach of EMD, empirical mode decomposition, has been extended in the literature for multivariate case. That is, there are various forms of this. That is complex empirical mode decomposition, rotation invariant complex empirical mode decomposition, bivariate empirical mode decomposition, multivariate empirical mode decomposition, fast multivariate empirical mode decomposition. And then actually here this multivariate form of this empirical mode decomposition, that also has some problem. Empirical mode decomposition, there are two problems. One is actually it lacks mathematical theory, and the second one, it has mode mixing problems. So like whatever these components you obtain using EMD method, these components sometimes they have multiple scales. So this there should be one scale linked with the component, but in practically when you use this algorithm, then there is a two scales are present in the data. So that is that is known as actually mode mixing problem. So this is motivated by that, this empirical wavelet transform was proposed in the literature, and we have actually used in this work empirical wavelet transform. Then we have extended it to multivariate empirical wavelet transform and an application for epileptic seizure detection for EEG signals. So human brain is actually very complicated and is highly nonlinear system. And electroencephalogram, which we call EEG, measures the electrical activity which is generated by the neurons in the brain. And epileptic seizures or epilepsy seizures are outcome of the transient and unexpected electrical disturbance of the brain. So in the actually brain, all neurons, they synchronize together and they generate actually very high electrical activity. And due to that, there is actually presence of high electrical current, and due to that actually everything disturbed. And the brain is the master of the body, and once brain is disturbed, then all activities of the actually body they are disturbed. So epilepsy is a very serious disease and it affects around 2% population of the world. And EEG signals, they are commonly used for diagnosis of epilepsy. And we have proposed empirical wavelet transform based approach for patient specific epileptic seizure detection using the surface EEG signals with the help of machine learning algorithms. So we will see machine learning algorithm together with this multivariate empirical wavelet transform, and nicely you can detect the seizures in automated manner. So here you can see this is the human brain, and it has 4 lobes: frontal lobe, parietal lobe, and then occipital lobe, and this temporal lobe. So these actually, these 4 lobes, they represent different regions of the actually brain, and whatever we do, this activity, it affects the different the EEG signals obtained from different brain regions. So whatever we do actually, this all have they are associated with one of these 4 regions. So now how to get this electrical activity generated by the different regions? So we use electrode cap. So here you can see this is 10 to 20 international electrode positions, and we put this electrode on this human brain, and then from the different channels we can obtain different EEG signals actually. And then here this is the one example where we see two channel EEG signal, and that is this is just example, and you can have 12 channels also, 28 also, 56 also. Depends on the electrodes. And now instead of using this channel-wise processing, we actually perform joint analysis of the signals for our developed method. So what is the motivation for empirical wavelet transform? This empirical mode decomposition actually suffers from mode mixing problem, and already I mentioned it lacks mathematical theory. So this empirical wavelet transform has been proposed recently to overcome these limitations of the EMD method. So basically, when you use this EWT, empirical wavelet transform, it has mainly three steps. One, actually we obtain Fourier spectrum in the frequency range 0 to pi for the analyzed signal by applying this fast Fourier transform algorithm, FFT algorithm. Then second step requires segmentation of the Fourier spectrum into n contiguous segments based on the boundary detection method. Then we define empirical wavelets at the bandpass filters on each segment. So from different this empirical wavelets as bandpass, they give you different components, which we call them intrinsic mode function IMFs. So our contributions include extension of this empirical wavelet transform method for multivariate signals, and also we propose time frequency representation of multivariate signals using empirical wavelet transform with application of epilepsy seizure detection. So actually we have proposed this empirical wavelet transform based multivariate time frequency representation for analysis of multi-channel signals. Generally, time frequency representation is used actually for single channel data, but here it is used for multi-channel data, and we have defined this time frequency representation for multi-channel data, and that we will see in this work. So if you apply this EWT, empirical wavelet transform channel wise, then each actually channel will have different frequency components, different IMFs. So in order to have same number of IMFs, what you have suggested, we take the average spectrum, Fourier spectrum of the all channels. So we determine the Fourier transform of each channel, and then we take the average of this Fourier transform, and whatever average spectrum we have, based on that actually we perform the boundary detection, and we determine the different frequency range. According to that frequency range, we apply these boundary detections on each channel, so that actually we have same number of components. And after that, we have all these components, obtained components, we apply this Hilbert transform that gives you an amplitude envelope instantaneous frequency, and in that way actually it has same number of components. And once you have this instantaneous frequency and instantaneous amplitude or amplitude envelope from the all components, then we can determine joint instantaneous frequency and joint instantaneous amplitude by using these formulas. And once you have these joint instantaneous amplitude, joint instantaneous frequency, and from that we actually determine multivariate time frequency coefficients in each oscillating level, which is computed by following expression. So that is actually, and this is for one specific frequency component, and then we generalize it for multivariate time frequency representation for all oscillatory levels, which can be represented by this mathematical expression. So this is actually a multivariate time frequency representation for this multivariate actually multivariate data or multi-channel data for all frequency components, all modes, all channels. So in this work, actually, since epilepsy, if you actually go to the hospital and these doctors, they generally detect epilepsy based on the amplitude level of the signals. So motivated by that, we have also proposed the features which are also actually associated with the amplitude value of the signal. So these features are defined as mean of joint instantaneous amplitude, which is expressed mathematically by this expression. and mean monotonic absolute amplitude modulation change, which is defined by this expression, and variance of monotonic amplitude modulation change, which is defined by the following mathematical expression. So these three mathematical expressions have been used to compute these three features which we have proposed. And this is actually proposed epileptic seizure detection algorithm based on the multivariate empirical wavelet transform and machine learning algorithms. So here you can see we have used PhysioNet CHB MIT scale PEG database, that is standard EEG database, which has recording from 23 patients and 23 channels. So here 23 channels, if you use EEG signals for 23 channels, then actually it suffers from a huge computational complexity. So in order to make our method suitable for real-time implementation, we have suggested channel selection criteria. So out of 23, we have selected 5 channels. So this the channel selection criteria actually includes selection of the first channel, which has least standard deviation, and after the other 4 channels have been selected based on the relatively higher mutual information with the first selected channel. So in that way, you have 5 channels, and then we apply this multivariate empirical wavelet transform on these 5 EEG signals, and then actually each channel has 10 components, and so these 5 channels, we have 10 modes. Then for each channel, from the different modes, we can determine standard amplitude and frequency for each mode, similar for 5 channels, and then joint standard amplitude and frequency of each mode is computed, and then we extract the feature from mode 1, mode 2, mode 10 till mode 10, and then these features actually we will see they require actually feature processing, because they don't give better discrimination between seizure and seizure-free intervals. So that actually, so we have proposed some feature processing, and once you do this feature processing, then you apply machine learning based classifier, then nicely you can classify this seizure and seizure-free intervals of the EEG, and it's kind of actually automatically you detect whether person has seizure or not. And so for example, person is driving a car, and based on such kind of method, you can detect in the early detection can be done, prediction of the seizure can be done, and that person can stop the car and take the drugs, and he or she can bypass the seizure attack. So it is very useful for the epilepsy diagnosis. This area is also known as computer-aided medical diagnosis, and this is actually computer-aided seizure detection can be carried out. And this is the example. Here you can see this is the 5-channel EEG signal, and this is the obtained multivariate time frequency representation using our proposed method. This is actually multivariate seizure-free EEG signal, and this is the obtained time frequency representation. And here you can see for seizure case, there is a presence of high frequency component as well as low frequency component. On the other hand, seizure EEG signal, there is presence of only low frequency component. So this is actually very important signature which can be used to detect the seizures, and nicely based signature actually, even by looking this pattern itself, one can detect whether this person has seizure or not. And like in rural areas, based on this pattern, we can decide whether a person is affected by seizures or not. And once it is seizure detected, a person can go to urban area for the further treatment. So proposed framework actually requires the feature processing also that I mentioned earlier. So these are the, here you can see the mean of joint distance amplitude in the left column, and there is the presence of noise. So we have proposed the moving average filtering for this each waveform of the each, and then this is actually processed after applying moving average filter. This is smooth actually these features, and the smooth features you can see there is improvement in the discrimination between seizure and seizure-free intervals. Similarly, for second feature, mean monotonic absolute AM change, and it's a filtered version, smoothing pattern, smoothed part of that, and third one is variance of monotonic AM change, and these are the featured, these are the moving average filtered part. And now actually then we see if you multiply all of them together, of these 10 modes, their features, then there is actually very nice discrimination between seizure and seizure free. So we have proposed HUDMUT, this smooth processed features can be multiplied together. So that is HUDMUT product can be performed in order to join feature vector. So this is actually this is the EEG signal, raw EEG signal, and the joint feature vector first, joint feature vector second, and joint feature vector third. So here you can see here this epileptic seizure actually is taking place, and that can be detected nicely with well localization and nicely good time localization, time resolution, instant, like a very precisely seizure detection can be done, and that is not possible in the raw EEG signal. We don't know, not clear where this event is occurring. But when you go in feature space, and nicely you can see actually that particular point, this is actually the seizure is taking place. Epilepsy attack is coming into actually into like consideration. So that is actually this kind of area in machine learning these days is known as explainable AI, explainable artificial intelligence. So where you can nicely understand what is actually feature, what the feature value, and what is the connection of the features with the disease that we are actually detecting. So nicely you can correlate the feature extent with the disease level. So the different level of the disease can be identified based on the different kind of actually value of these features. So this explainable AI can be carried out, and these features can be given as an input to machine learning classifier. So here is random forest classifier is used for actually automated identification of the seizures. And in this table you can see actually people have used various machine learning algorithms in the literature, various signal processing techniques, and different cross validation, tanning rate, and our proposed method, which is actually based on 3 features extracted from different oscillating labels using multivariate extension of EWT. And out of 23 channel, we have used only 5. In other case, you can see in this table, in the people, sometimes people have used 23 channels, sometimes they have not mentioned how many. So our proposed method, which is based on 10-fold cross validation, and it gives you 99.57% specificity and 97.91% sensitivity and 99.41% accuracy for the epileptic seizure detection using surface EEG signals. So this is actually one part, and the second part is the improvement of this empirical mode decomposition. One approach was this empirical wavelet transform, and second approach that was iterative filtering. So actually we have also used this iterative filtering here, and we have extended this for multivariate framework, and after that we have applied this multivariate filtering for schizophrenia diagnosis. So that actually that we will see in this part of the talk. So iterative filtering technique actually, like we see in empirical mode decomposition, we get the first IMF, the highest frequency component. After the second IMF is the lower than the highest one. So like that, from high to low frequency components are represented by the first to the last IMF. So the same concept here we apply based on the filtering approach, but filtering actually it depends on the maxima and minima of the signal, and that is actually like it uses same concept. So the iterative filtering technique subtract out the selective part of the spectrum in order to obtain the mode one by one iteratively, and this L equals to alpha capital N upon K. So this N is the sample size of the data, K is the number of extrema, and this L, this is actually that is the length of the filter. That shows if you have a number of extrema more high frequency component, then your L will be less, and if you have less extrema, then L will be more. So this cutoff frequency is inversely proportional to the length of the moving average filter. So here, and that alpha is equal to 2, that is a suggestion in the waste paper, and based on that actually we select the filter length, cutoff frequency of the filter, and then actually we subtract this from the signal, and then the residual, that actually residual, then we perform many iterations, and the residual becomes the first IMF in that way, and then Similarly, we subtract the first IMF from the signal, and then we do this for many iterations, then we get second IMF, so that we can get all possible IMFs from the signal. So this is very simple example. Here you can see for iterative filtering. So this signal has 3 frequency components, and this is the actual design filter. So from this filter, this is the filtered signal, and filtered signal now subtract from the signal spectrum. These all are in frequency domain. So when you subtract these 2 frequency components, then you will have last frequency part is IMF. So first IMF will have the highest frequency component. Now, in order to have second IMF, we subtract this highest frequency component from the spectrum. So now spectrum will have 2 components only. Then again you determine this filter, and based on the filter, and we subtract out this first frequency component, the second IMF will remain have only this second highest frequency component. So this first IMF, second IMF subtract from the signal, then you will have the highest frequency component that present in the signal. So that will become the third IMF. So in that way, actually, we are removing different frequency component from the high frequency to low frequency, and nicely actually we can have different IMFs from the signal. So now this process of iterative filtering, in left hand side you see this is univariate iterative filtering method, can be explained by the flow chart, and this actually this also can be extended to multi-channel with the actually nicely the concept of this the maximum number of maximas. So that is suggested actually concept. If you don't use this concept, if you apply this iterative filtering channel wise, then each channel will have different number of components. So what we have suggested, this whatever this maximas, this number of extremas that you are using, so you use determine the number of extremas for each channel, and then determine the maximum of that. According to that, you design the filter length, and then you determine the cutoff frequency, design the filter, and use that filter for all channels together. So in that way, you will have same number of frequency component from each channel. So here you can see this univariate, you have signal, then determine the number of extremas, then determine the filter length, then filter length you determine the filtered signal, subtract this filter from the signal, then you have residual, then you have 2 stopping criteria. First, the threshold is greater than 0, then you continue. If your number of extremas greater than 3, then you continue. If these conditions are not satisfied, then you stop the process, and that way you can have different number of IMFs. Now, in order to have this multivariate iterative filtering, we have signal, then determine the number of extrema for each channel, then determine the maximum of extremas, and then that is actually from that you determine the length of the filter, and then filtered signal, subtract, and then based on stopping criteria, you have nice multivariate iterative filtering. So this is one nice example. Here you can see this multivariate iterative filtering for bivariate data. So here you have 2 channels, and in this case, actually these IMFs, they will be multivariate in nature. So this is 2 channel data, and first channel has 2 IMFs, second channel has 1 IMF. But now when you apply this multivariate signal processing, then it will work a different way. So what we do, we determine the filter length. So first channel, this is the filter design filter, and for second channel, this is the design filter. So we take the highest of both for both channels together. So the highest of both actually these channels filters will be the first one, which we will use for filtering. So when you apply this filtering, then actually then you have the first channel, this is the highest frequency, and the last one no frequency. So this is actually first IMF. Now first IMF will be subtracted from the signal, then the residual, then we design the filter. So this is the highest frequency, cutoff frequency from both the filters. So this is the selected filter for both channels, and this is the obtained second IMF. After that first IMF, second IMF, both will be subtracted from the signal, and then we have residual. So here you can see this is a residual, and now we will determine the filters. So now both filters are concentrated around 0 frequency. So the maximum will be same. So now this whatever signal spectrum we have, that will become third IMF. So in that way you can say first IMF, second IMF, third, both are bivariate integral mode functions. And one nice application of this concept can be seen in real life scenario for like ECG and respiratory signal is correlated to each other. And in ICU, we actually record such kind of signals, various medical signals, in order to have reliable estimation of various measurements like heart rate. So here you can see there are four actually biomedical signals recorded in the ICU. The first one is the ECG from the first lead, and second one is ECG from the second lead, and third one is respiratory rate or breathing signal, and the fourth one is seismocardiogram signal taken from the database. So here actually physiolite database. So now these four signals, they are two different actually, they represent different characteristics. But good thing is that when you apply this multi-channel signal processing or multivariate iterative filtering, then each actually correlated part of the each waveform can be represented by the different oscillating mode, different IMFs. So here you can see when you apply this this four ECG, one ECG2, first lead, second lead, breathing, seismocardiogram, then this 11th IMF shows the same frequency component which is present in all these four different biomedical signals. So that is actually one of the beauty of this multimodal approach, where actually multivariate signal processing can give you the very meaningful information, correlated information from the data which is actually coming from the different parts of the body or different sources. So that is nicely correlated part can be obtained. So now we have applied this actually concept for schizophrenia detection from EEG signals. So schizophrenia is a chronic and severe mental illness and affects 20 million people worldwide and 1% of world population and more than 1 million people in India. And the symptoms include hallucinations like fixed fast belief, hallucinations, experience of seeing, hearing, tasting, smelling or feeling, which does not really occur, disorganized speech and thinking, abnormal motor behavior. So that is actually symptoms of this schizophrenia. And this is the proposed approach that we have suggested for the schizophrenia diagnosis using the signal processing machine learning techniques. So we have M channel, then we have perform segmentation of 25 seconds. Then we apply some pre-processing. So the EEG signals actually they contain undesired frequency components, and by using this pre-processing, these can be filtered out. Then we apply iterative filtering for multi-channel EEG. And then for the different channels, we use the different modes, mode 1, mode 2, mode N. And then actually the this very innovative actually way where we have actually we have represented these rhythms in multi-channel data. So like the conventional way, people use the rhythms of the single channel data, but here these rhythms are defined for multi-channel data. This is also actually you can take this as a direction of the research. You can apply an issue of like single channel, you can apply multi-channel rhythms and then use machine learning approach. And so multi-channel rhythms can be obtained here. Then we can extract features from EEG rhythms. Then classification is performed, which gives you the nice actually separation between healthy and schizophrenia patients. So that is very good for the diagnosis of schizophrenia. So publicly available data set of schizophrenia from Institute of Psychiatry and Neurology, Warsaw, Poland, has been used in this study. And in this 14 patients they have used for the schizophrenia EEG recording, which includes 7 males and 7 females. And similarly for healthy case, we have 14 healthy subjects, 7 males and 7 females. And 90 channels have been used to record the EEG signals with sampling rate of 250 Hz, and the duration is around 15 minutes approximately. So this is actually, now you see multivariate filtering decomposition of EEG signal. So these 3 channels have Z, CZ, PZ, and then these are the obtained, like for just example, second, third, fourth IMFs are shown. But the difference is that now they are multi-channel IMFs. So each IMF is now having actually 3 IMFs. Then these are the power spectral density plot of these actually different IMFs. And then you can see these IMFs, they are showing the actually same frequency components. It's clear from the time domain representation, also clear from the frequency domain. because they are actually mode alignment properties preserved. And then we have separated rhythms using this actually rhythms frequency range. So what we have done, we have got the IMFs from this multivariate iterative filtering, and each IMF we compared, we determine the center frequency or mean frequency, and if it is between 0.1 hertz to 4 hertz, then we selected this for combining both data rhythm. If it is coming between 4 hertz and 8 hertz, then we consider this part of theta rhythm. So whatever these rhythms are coming between 0. hertz and 4 hertz, their center frequency, we have combined all such components, IMFs, to get the delta rhythm. Similarly, all IMFs whose center frequency is varying between 4 hertz to 8 hertz, then we combine all of them to get the theta rhythm. Similarly, alpha rhythm, beta and gamma rhythms are obtained. And here you can see these are the multi-channel rhythms. So this is actually one of the unique kind of rhythm separation, where you have multi-channel signals, you can have multi-channel rhythms. So delta, theta, alpha, beta, gamma rhythms can be separated out. And then we have actually used the feature extraction process. So Hazoth activities or mobility and Hazoth complexity, they have computed as a feature set. So now total feature corresponding to a trial, so number of channels are 19, rhythms are 5, as well parameter 3, so total 285 features are there. And this is actually huge number of features. So in order to have a less number of features or statistically significant features, we have proposed this student t-test. So based on the probability value, we have actually selected the best features. So this table shows the most significant 10 features, and these best 30 features are used for the classification purpose. And this is shows the actual box plot, so the box plots for this most significant 10 features are shown in this, and box plot shows the clear discrimination between these two classes based on the different features. So this shows that actually these features, whatever we have used for classification purpose, they are also actually discriminatory in nature. So this is actually there are a lot of research these days. People are using deep learning, convolutional network-based classifier, where features are extracted automatically. But such kind of direction, where you extract feature from your side, they are statistically significant features, and they can actually tell you a lot of information about the data that you are analyzing. That is, so this interpretation can be done together with the classification. So signal analysis is a very important part in order to have nice interpretation. And otherwise, it will be just a black box and classification is going on, and you don't know what is going on inside. So after that, different classifiers are trained using best 30 features in order to differentiate each signal corresponding to healthy schizophrenia. So based on a trial and error method, we have selected 30 features, which has provided 98.9% classification. After that, it is not increasing. So we have selected these number of features for the classification purpose. Then we have used the following classifiers: SVM cubic kernel, SVM with quadrature kernel, SVM with linear kernel, linear discriminant, k nearest neighborhood classifier, distinct classifiers for the classification purpose. And the performance of different classifiers have been evaluated using the following parameters, which are accuracy, sensitivity, specificity, and positive predictive value. And mathematical expression of these performance measures can be seen from these mathematical expressions. So we have actually in this table we have shown the performance parameters of different classifiers with best 30 features. So you see the different 5-fold, 10-fold cross validation with the SVM, cubic, SVM, quadrature, SVM, linear discriminant, KN, and DCMT classifiers, and accuracy, sensitivity, specificity, positive predictive value, area under ROC curve, and together with mean and actually standard deviation can be seen. And from this table, it is clear that this SVM with cubic kernel with a 10-fold cross validation process actually provides the better classification performance. So then we have compared our proposed method with other existing methods in the literature, and in this table you can see people have used deep convolutional neural network, SVM, radial basis function, this classifier, support vector machine, CNN, various different classification. Our proposed method that is based on algorithm features and extracted from the easy rhythms obtained from each signal using this multivariate filtering based approach. And SBM is cubic with cubic kernel classifier is used for classification. And here you can see this accuracy that we have got 98.90%, sensitivity 99.00%, specificity 98.80%, and area under ROC curve that is actually 0.999. So area under ROC curve that is actually one is the classical, one is the ideal limit and is near to one. So it's our proposed method has given actually best classification performance. So this is the actually conclusion of this talk. Proposed multivariate empirical wavelet transform and multivariate iterative filtering are able to decompose this multi-channel and multivariate signal into meaningful components. And mode alignment is the most important properties of the multivariate decomposition techniques. And the proposed methods properly align the similar oscillatory components across different channels. And the proposed methods have provided good detection performance for diagnosis of epilepsy and schizophrenia based on the scale PG signals. The proposed automated approaches can be useful for assisting neurologists in their decision makings. And computer smartphones with the proposed algorithm can be used for diagnosis of these neurological disorders in rural areas where we have shortage of doctors. And these days, actually, most of the people actually in India, everybody is using a smartphone. And using a smartphone, does that mean that you are smart? If this smartphone is able to do smart work, it can do smart health monitoring, then you are really smart. So then you use these methods in the form of algorithms, form of software in the smartphones, and then really smartphone will become really smart, and that is very useful for the health. And this actually, this presentation is based on these two our recently published papers. And if you are more interested in the details about these presented methods, I request all of you to please go through these two papers. And if you have any questions, please feel free to write me. So thank you very much. If you have any questions,
Thanks a lot, sir, for sparing your valuable time and for having an informative session in this FTP. Sir, there is one question from the participants that if someone has to work on these two problems, so from where we can collect the data set?
Yeah, these actually, whatever these two papers, whatever results I have presented, they all both are publicly available databases. They are standard databases, they are available on internet.
Okay.
So you go through these papers and you will find their source.
Right, sir. Right, sir. Right, sir. So one thing has one participant has also mentioned: is it possible to collect the primary data set for these problems if someone is a machine learner? So whether it is possible or not?
What, Dr. Saurabh?
Means for computer students, is it possible to collect the primary data set for these problems? Hello.
Yes, yes.
Yes, sir. Someone is saying that whether it is possible to collect primary data set.
Yeah, private, like a recording.
Means from hospitals or from some.
That is what actually some of the work actually now we are doing. So we are recording our own database that we call private database, and this is publicly available database. So these databases are also recorded actually in the hospitals. That is not a synthetic database. So like whatever results I have presented, that is also like Poland and other one like CHB, MIT. So they have also recorded database from the subjects of the patients. But Indian patients are different. So actually, and they are American patients, they are German patients, they are like they may be Poland patients. So Indian patients actually we are recording data. And some databases are already like some of the recently from IIT Delhi, some groups they have made this publicly available database, but they are reported from the Indian patients.
Right,
and
sir.
we are also working on that. We are recording now the signals from the our patients from our country, and we are applying these methods to validate them. So it is not very difficult to record data, and these days the easy recording system is very compact, and this is emotive that looks like ear belt and
Right.
easily data is like wireless system. just you put the electrode cap and automatically the signals will come in the computer or your mobile. Then you can process them using this MATLAB.
Right, sir. Right, sir. So, any other query? So I think these are the queries which have been addressed by Professor Ramvilas Pachori, sir. So, sir, once again, I'm very thankful to you. You have spared time for us and for sharing the informative knowledge with the participants of this FTP. Thanks a lot, sir.
Thank you. Thank you.
Thank you, sir. Thank you so much, sir. So, dear participants, this was the session 6th in this 1 week FTP. Now we'll meet tomorrow at 11 a.m. We have 2 sessions tomorrow. First is at 11 a.m. and second is at 2 p.m. And I'm just sharing the attendance. Just a minute. Yes, I have pasted it in the chat box. So you are requested to mark the attendance. And this is the attendance for session 2nd of today. And now we'll meet tomorrow at 11 a.m. Tomorrow, again, we have 2 sessions. So I will share the details in the WhatsApp group. Thank you so much. Have a nice day.